This presentation is delivered by the Stanford Center for Professional Development.
All right, so one real quick point before we dive into the main meat of the lecture. It's just a clarification on something we did last time called a cast. So remember last time where we had a cast, which was this thing that allowed us to say treat this one data point or this one data item, this one variable, as a different type for one particular operation. And so last time I told you you could actually do something like int x equals, let's say we had some double up here, like double y. And maybe y got set to some value like 3.5. And I said you can do a cast like this. And we put y here, right? And so that'll take y, it'll truncate it, right? It drops everything out of the decimal point and assigns it to an int. And I sort of said, misspeaking actually, that you could drop this part. It turns out that in Java, anytime you do a cast to something that loses information, like when you go from a double to an integer because it truncates, it drops everything after the decimal point, you have to put in the cast. So you have to make this explicit. If you go the other way around where you're not losing information, like if you were to have y equals x at some point where you know that x is an int and y is a double, you're not going to lose information by assigning an int to a double. So there you're okay. You can do the explicit cast if you want, and actually I would encourage you actually to use the explicit cast. But in this case, you don't need it. In this case over here, you actually do. So when you lose information, you need to make an explicit cast. For most of you, it probably will not affect your day-to-day life, but that's just something you should know. Alrighty, so any questions about anything we've done up to now? We're just going to kind of press ahead with something that we talked about last time. Remember last time we were talking about our friend the while loop? And the while loop was something that you used when you don't know how many times you're going to do something. This is what we refer to as an indefinite loop, not an infinite loop, right? It's important that you have the DE in there. Infinite loop keeps going forever. But an indefinite loop is one that when it starts out, you don't know how many times you're going to do something. You're just going to do it some number of times. Well, it turns out there's times in life where you're going to do something some number of times. You don't know how many, but you figure you probably want to do it at least once. Okay, this was kind of the case with my brother going to college. Like he figured, I'm going to go to college, but when he got there, he didn't know how many degrees he was going to get. And he just kept going and going. And 5 degrees later, he was kind of like, okay, I think I'm done now. So that was his while loop, right? He didn't know how many times, but he knew he wanted to do it at least once. Now, the interesting thing is that in programming, this actually happens fairly commonly. So I'll show you a quick example of this if we go over to the computer. There's something we call the loop and a half, because in some sense, you want to do half of the loop at least once. Okay? Think about it this way. Let's say we want to take some program that reads in a bunch of numbers from the user until the user enters 0 to stop, and it kind of computes the sum of all those numbers. So it adds them all together. So we might have basically some sentinel value, right? We're going to use our constant, our little friend last time that we talked about the constant, to define what is that value that the user enters, in which point they want to stop entering values. This in programming speak is often referred to as a sentinel. It's kind of the last thing I'm going to give you that tells you I'm done, I'm not going to enter any more values. But until I give you that sentinel, I'm going to give you a bunch of values that I want you to add together, for example. So that sentinel we might define as a constant, and so we could have some loop that says, well, if I'm going to keep track of some total or some sum of all the values you enter, that total is going to start at 0. I'm going to ask you for some value, so I'm going to read in some integer and store it in the little box named val, right? So I just declared a variable. And then I'm going to have a loop. And what my loop says is, if the value you gave me is not the sentinel, that means you don't want to stop yet, right? So I have a logical condition in here that's checking against the constant, and that's a perfectly fine thing to do. So we're taking a lot of those concepts you saw last time and just kind of sticking them all together into one bigger program. If I haven't seen that sentinel yet, then take the value you just gave me and add it to my total and store it back into total using the little plus equals shorthand you saw last time, okay? Then what I need to do is, after I've done this, I need to ask you for a value again. So I say value equals readint. Notice I already declared the value up here, right? I already declared this variable up here. And this guy's lifetime is until it gets to the closing brace at the level at which it's declared. It's not declared inside the while loop, so this closing brace doesn't make it go away. This closing brace makes it go away, which means it's actually alive the whole time in the while loop, and it's perfectly fine. So val, I read in some other value from the user, and again, I go back through this loop. Did they give me 0? No, add it in. They give me 0? No, add it in. And when they give me 0, then I say, oh, the value is equal to the sentinel, so this test becomes false, and I come down here and I write out the total as total. And you might say, oh, okay, Maron, that's fine. What's wrong with that? Well, in computer science, or actually in computer programming, we really hate duplicated code. If we can avoid duplicating code, even if it's one line, we generally try to do it. And you can see there's a duplication here, right? What's happening is there's something we wanted to do at least once, which was to ask the user for some value. But we need to keep doing that over and over in the loop, even after that first time. So we kind of run into this conundrum where we say, are we going to have to repeat code? And there's a way around this. So the way around this is we pop out that piece of code, and we're going to pop in our friend, the loop and a half. Okay? And so what the loop and a half says, the first thing that looks funky about it is we say while true. And you see that and you go, oh my God, right? Anytime you see while true, you're thinking, bad times, right? I'm never going to break out the loop. Every time I come here and evaluate the condition, it's always true. Isn't this an infinite loop, Miron? And it would be, except for one caveat. And here's the caveat. We're going to ask the user for a value, right? Notice we declare the int val inside here. We could have declared it outside if we wanted to, as long as we didn't do the read int outside. We could have just said int val and declared it out here. But we're only going to use it inside the loop, so we're just going to declare it here. We read an integer from the user. We ask if the value is the sentinel. If it is, we break. What a break statement does is it will break you out of your closest encompassing loop. What does that mean? It means it finds whatever loop is the loop you're currently in and jumps you out of just that loop. So if you hit a break statement, it will jump out to essentially the place right after the closing brace for that loop and keep executing. So what it allows you to do essentially is to check the condition to break out of a loop in the middle of a loop, which is kind of a funky thing rather than at the very beginning or every time you iterate through. So we get the value from the user. If the value is the sentinel, we break, which means we never execute this line or the rest of the loop. We jump down here. If it is not the sentinel, then we add to the total while is true, so we execute the loop again and go and read another value from the user, right? So notice that this read int line is no longer repeated. We only do it once. But because of the structure of this, we're always guaranteed that this portion of the loop up here is always executed at least once because we add a while true, and we're checking the condition to break out the loop in the middle, okay? Now, one caveat with that is, in terms of programming style, it's generally a bad time to have multiple of these kind of breaks inside a loop, because it makes it very difficult for a programmer to figure out what condition has to be true to break out of the loop. If there's only one place you see a break, then there's only one condition you need to check to break out of the loop. If you have multiple statements, multiple if, blah, 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 break in your loop, that means the programmer has to keep track of multiple possible places you could have broken out of the loop in their head, and that gets pretty dicey. So you generally want to avoid that when you're doing it. Okay? So any questions about the loop and a half?
Is it okay to redeclare a variable in a loop like that over and over again?
Yeah, it's fine to actually declare that variable inside the loop. You don't need to worry about like efficiency issues or anything like that. So let me show this to you in action in a larger program, right? So here it is. Here's that loop and a half in the context of an actual run method. It prints something on the screen. It sets total to be equal to 0. And then it comes in here, while true will always execute, right? Because the condition's true. So it asks the user for some value. We enter 1. 1 is not equal to the sentinel. So we add that to the total. And you can see here it's keeping track of value and total. Here's just my 2 declared variables and the little boxes for them. And they get updated as I go along. So while it's still true, I read another value. Let's say the user gives me 2. I add it to the total, which is now 3. And I come back up here. I'll go through this a couple more times. Okay? User gives me 0. Now notice when the user gave me 0 here, I hit the break because my value is 0 and that's equal to the sentinel. So it says, hey, the if part is true, so do the break, and it immediately jumps out to the end of the loop. It did not do, even though total changed this value. So I feel like a little like Roger Daltrey when I'm doing this. Anyone know Roger Daltrey, lead singer of The Who? Go look it up on Wikipedia and watch the video. Man, I'm feeling old. All right, and then it says the total is. So this total plus equals value. The value just doesn't get added that last time, even though it would have been a 0 and wouldn't have affected things. It would be different, right, if we set the sentinel equal to -1. Then you would actually see that the total didn't get 1 subtracted from it. We could have set the sentinel to whatever we wanted, but in this case we use 0. Okay? So that's our little funkiness, and it writes out the total as 0 for actually doing the loop and a half. Now, in terms of doing all this stuff, okay, you might think, well, hey, Maron, you showed me about the for loop last time. You showed me about the while loop. It turns out I can write the same loop in equivalent ways using both of them. So remember, the for has the initialization, the test, and the step. The initialization happens once. Then the test happens every time through the loop. And then the step happens kind of every time at the end of the loop. That would be exactly equivalent if I wrote it like this. The init happens once before the loop. I have some while loop that checks the same test. I have the same set of statements that would be in the for loop body, and I do the equivalent of the step in the for loop at the very end of the loop. So these two forms are exactly equivalent to each other. And you might say, hey, Marin, if they're exactly equivalent to each other, why do I have these two loops, and when do I use one versus the other? Well, for for loops, you want to think about what we refer to as definite iteration. That means we generally know how many times we want to do something, and that number of times we want to do something is how we sort of count in our test. When we don't know how many times we actually want to do something, that's an indefinite loop or indefinite iteration, as I just talked about. That's when we use a while loop, when we generally don't know how many times we're going to do something. Okay? So that's kind of why we give you both forms. And most programming languages actually have both forms. But to a programmer, it's more clear between seeing the difference between for and while is kind of the meaning of it, right? Are you counting up to something some number of times, or are you just going to do something until some condition is true? That's kind of the differentiator there. So any questions about loops? So let's put this all together in the context of a bigger program. Okay, so I will show you a bigger program here. So we'll come over here. Here's a little program. Let me just run it for you real quickly. Come on. So we run along, and what this program is going to do is draw a checkerboard, right? Just like you're used to in the game of checkers or chess, a little checkerboard on the screen. So this is going to be a graphics program. It's going to draw a bunch of G-rects, right, which are just rectangles. In this case, they're going to be squares to draw a little checkerboard. And you should think, this might have some similarities to maybe some of the stuff you're doing in your current assignment. Yeah. So let's go through this code and see what's actually going on. And we can put a bunch of things we learned together, like constants and loops and blah, blah, blah. So what's going on over here is, first of all, we start off with a couple constants, right? And the constants we're going to have tell us how many rows and columns are going to be in our checkerboard. We want to draw a standard checkerboard, which is an 8x8 checkerboard. So we have private static final int n rows is 8, and private static final int n columns is also 8. Notice that these two constants are not defined inside a method. They're defined inside the class, but not inside a particular method, which is generally where your constants are going to be defined, right? In a class, but not inside a particular method. And then for the run part of the program, first thing we need to know is we need to figure out, because we want this thing to be general, right? No matter how big our window is, we want to draw a nice little checkerboard. So we need to figure out how big do those squares on the checkerboard need to actually be so they appropriately fill up the screen. How do we do that? We get the height of the graphics window. Remember our little friend, the method getHeight, which tells us how many pixels high the graphics window is. And we divide that by the number of rows. Since we divide that by the number of rows, this is going to give us integer division, right? This is going to give us back an integer, and we're going to assign that to square size, which is an integer. So everything's perfectly fine, because this is some number of pixels. This is an integer, and so this is an integer value divided by an integer value gives you an integer division. So that tells you basically how many squares can you fit in sort of the height of the screen. And that's going to be the size of one of the sides of our squares. And as you know, squares have the same sides on both sides, same length on both sides, so we're perfectly fine. Now what we're going to do here is, we want to get the structure that's like a grid. In order to get a grid, we're going to have what we refer to as a pair of nested loops. All that means is one loop is inside the other loop. Okay, so we have two for loops here, and you can see with the indenting, one is kind of nested inside the other one. So one is going to count through the number of rows. So we're going to have one loop that's going to go through the number of rows we want to display, and another loop that within each row is going to essentially count the number of columns in that row, because we're going to put one box for every little square grid on there, which means for every row we need to do something for every column in that row. So we're going to have one for loop that's going to have I as what we refer to as its index variable. So remember when we talked about for loops and we talked about counting, we said, oh yeah, you say something like int I equals 0, I less than num rows. And that'll count from 0 up to num rows minus 1, which iterates num rows times, or n rows times. That's great. The only problem is this variable I, remember, is alive until it gets to the closing brace that matches this brace, which means that I is alive all the way to down here. Well, if that I is alive all the way to down here, if we have some other for loop in the middle, if it's also using I, those I's are going to clash with each other, and that's bad times. So what do? We just use a different variable name. What we're going to do is, what's the next letter after I? J, right? So I, J, and K you'll see are very popular names for loops. And those are the one place where descriptive names, you don't need to have some big name like, oh, this is the counter through rows variable or something like that. I and J are perfectly fine because most programmers are used to I, J, K as the names for control variables or index variables in loops is how we refer to it, because this is what the loop is using to count through. So we think of it as the loop index. So we have one here for j, and notice all the places I would have had I are now just replaced by j. So j gets initialized to 0, we count up to n columns, and j++ is how we increment j. So common error with nested loops is you have the same variable up here as you had down here, and that's generally bad times. Okay? Now, once we're counting through all the columns, the thing we need to figure out is where is this square that we're going to draw going to go? What's its xy location? Well, its xy location says, well, first of all, if you want to figure out its x, that's sort of going horizontally across the screen, right? Going horizontally across the screen depends on which column you're currently in. So I take j, which is the index variable for this loop over the number of columns here, and I multiply it by my square size. What I'm essentially saying is move over in the x direction j many squares. That'll tell you where the x location is for the next square that you're actually going to write out. Similarly, y, which is the vertical direction, I need to figure out which row I'm in. Well, I is what's indexing my rows, right? So I'm just going to take I and multiply it by the square size. That tells me how far down the screen I need to go to get the y location for this square. So now I have the x and y location. Any questions about how I computed the x and y location? Don't be shy. All right. Are you feeling good about x and y? If you are, nod your head. All right. I'm seeing some nods in there, some blank stares. If you have no idea what I'm talking about, nod your head. All right. That's better. There's always this indefinite ground where it's sort of like no one nods and they don't give you any feedback. So I'm begging you for feedback. All right? We could have put this outside of the j loop and just compute it, or we could have put the y location outside of here and just computed it once, because that y location will remain the same for the whole row. So that would have been an interesting little optimization we could have made, but we didn't make it here because I just wanted to compute x and y together so you would see them computed together, and because their forms are pretty similar to each other. Okay? So once I know the x and y location for that square, I need to say, hey, get me a new square at that location. So I say new grec. That gives me one of these new square objects. Where's the upper left-hand corner for that square? It's at the xy location I just computed. How big is the square? Square size width and square size height, right? Because it's a square. It's got the same width and height. So that gives me a new square. Now I got a square at some location that I want to display that square at, right? Because I compute the right x and y. The only problem is that it's a checkerboard. Some of the squares are filled. Some are not filled. How do I figure out which squares should be filled? This is where I do a little bit of math and a little bit of Boolean logic, and it just makes your life kind of beautiful. So rather than having a whole bunch of ifs in there and trying to figure out, oh, am I on an odd square or an even square, which row am I in, blah, 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 you do a little bit of math. And you figure out your math and you say, hey, you know what, that very first square that I draw in the upper right-hand corner, okay, let me see if I can bring that little square back up again. So I'll run this one more time. This guy up here, I can think of that square all the way up there as the 0, 0 square. That guy's not filled. But if I were to move 1 over, that is filled. Or if I were to move 1 down, that is filled. So if I think about the index location that I'm currently at, and I take my x and y coordinates, or I should say my I and j variables, because that's what's indexing my rows and my columns, and add them together, if that puppy's even, then it's not a filled square. If it's odd, then it is a filled square, because the very first one is 0, 0. That one's not filled, so even's not filled. But if I move 1 in either direction, I get something that should be filled. If I move 2 in either direction, I get something that should not be filled, etc. So the way that translates into logic for the code is I come over here, and it looks a little hairier than it actually is, but I say take the I and j and add them together and mod it by, or I should say remainder it by 2. Right? If I remainder by 2, if that remainder is 0, that means it's even. If the remainder is 1, that means it has to be odd. The remainder can't be anything other than 0 or 1 when I'm taking the remainder dividing by 2. So if that remainder is not equal to 0, that means it's an odd square, right? Because my remainder divided by 2 is not equal to 0. It means it was equal to 1. What I'm going to do in that case is I'm going to set filled. So this looks very funky. You might be inclined to think, hey, shouldn't you have an if statement here and say if this thing is true, then set filled? Well, think about it, right? If this thing is true, set filled will become true, and I'll get a filled square. If this thing is false, set filled will become false, and I'll get an unfilled square. So it works for me the way I want it to work in both cases. So rather than worrying about all this control logic for an if statement or all this other stuff, I just take my condition here, which is this big honkin' Boolean expression that evaluates the true or false, and just stick it in for the value for that set filled is actually expecting. And this will give me the alternating effect for squares. And when I finally do this, I need to say, hey, you know, I got that square. It's filled the way I want it to be filled. I know its location. Throw it up on the canvas for me, so I add it. And then I just keep doing this over and over, and I get all of my, for every row, I'll get a line of squares across in all the columns, and then I'll come down to the next row, and I'll just keep doing this until I get 8 rows of squares. Use the mic, please. That'd be great. Thanks.
How do you designate it as a Boolean expression? Does it just automatically assume that it is going to be true or false? Or?
Right, so that's a good question. The key that's going on here is this little operator right here, the not equal operator. Right? The not equal operator is a logical operator, which means it's going to have two arguments that it works on, and what it's going to give you back is true or false. So the way it knows that it's Boolean is that this particular operator, the not equal operator, always gives you back a Boolean value. Right? Just like greater than or less than, all those operators are Boolean operators that give you back a Boolean value. Whereas the stuff I'm doing over here, right, is just math. This is giving me back an integer, and I'm comparing that integer with another integer using a Boolean operation. That's why I get a Boolean. Does this only, well, this will work in any case as long as the window is wider than it is tall, because the way we compute the squares is based on the height as opposed to the width. Okay. No, that's different, and we'll get into that now. Well, the private part's the same, but I'll show you what all of those things mean in just a second. So we're going to do methods in just a second, and they'll become clear. Because everything's in terms of pixels, and the pixels are always integers. So we just want to compute in terms of integers, because all of our values we know are integer values. So let me push on just a little bit. Question right there.
Why are we doing it this way if we're supposed to be using top-down programming? Isn't this like the opposite?
Well, in this case, top-down programming is how you break things up into smaller functions, right? Here we only have one function. So we could actually think about, oh, should I do one row at a time? And that would actually be an interesting decomposition, is to have a function or some method that does one row for you, and I iterate that some number of times. And the reason why we didn't do it that way is we haven't done methods in Java yet, which is the next topic we're going to get into. So thank you for the segue. So the next topic we're actually going to deal with is our friend the method, but in the Java world. So hopefully methods, you've already seen in Carol, right? You saw how to break things down in Carol, and we did decomposition in Carol. And now it's time to bring that into the Java world. Okay? So when we think about methods in Java, you already saw a couple of these things, right? Like readInt, for example, is some method that you've seen. And so we might say, you know, int x equals readInt, or println is some other method you've seen, right, that just prints out a line. Now, one way we can take these notions and make them a little bit more familiar is, first of all, we can say the idea of a method is just like in Carol. You want to use methods to be able to break down programs into smaller pieces that you can reuse. That's critical. But in Java, they get a little bit more complicated. And here's where the complexity comes in. And it's easiest to draw the notion of how they differ in the Java world by thinking about mathematical functions, right? So somewhere, someday, which you're never going to have to worry about again as long as this class is concerned, is you learned about this thing called the sine function. You're like, oh, Maron, you told me there was going to be no calculus in here. Yeah, don't worry. This is just for this example, and the sine function goes away. You never have to worry about it again, at least for this class. Right, but the way the sine function worked is it took some value that you computed the sine of, right? So there was something here like x that you took the sine of, and what you got back from the sine function was some value that was essentially the sine of x. So you not only had something that we call a parameter, that was what that function was expecting in terms of information going in, you also got some information coming out, which is what the value of that function returned to you or gave back to you. Okay? That's the one bit of additional complexity that comes up with methods in the Java world as opposed to the Carol world. In the Carol world, you didn't have any parameters that went in and no values came out. In Java's world, you do. Okay? So first of all, just to wrap up on the little math example, a couple people asked last time about some mathy functions, and it turns out if there's this thing you import called java.lang.math, there's a bunch of mathematical functions you get in the Java world for free. And some of those are, for example, a function you might be using on this next assignment, like square root. So if we have double, let's say y, or I'll say double x. Double x equals 9.5. And then I might have some other double y here, and I want y to be the square root of 9.5. I would say math.sqrt, which is the name of the method for square root, and then I give it the value. Or I give it a variable whose value I want to compute the square root of. So this guy takes in something of type double, computes the square root, and gives you back that value that you can now just assign to some other double, for example. Okay? And there are some other ones in there. There's a power function. Someone asked about power last time. That's where you also get the power function. It's also in there. But power gives you a nice example of you can have multiple parameters. So power, you actually give it an x and a y. And what it does is computes x to the y power. So it's essentially computing something that would look like that if we were to write it out in mathese. And it gives you back that as a double. So we could assign that somewhere else. But notice we have two parameters here, and they're separated by a comma. Okay? And that's how generally what we're going to use to separate parameters is commas, just like you saw when we created, for example, objects over here. Right? We created a new grect, and we had to give it 4 parameters. They were just separated by commas. Same kind of idea going on over here. Now, the question comes up, what's the whole point of having, these kind of functions exist in the Java world, or methods in general? And the critical part about methods in Java, there's the whole notion of decomposition and top-down design. That's part of it. That's not the most critical part. The most critical part has to do with a notion we think of as information hiding. Okay? So what is information hiding all about? The real idea, the way you can think about this is that everything in the world is a function or is some method. So for example, anyone know what this is? CD player. You're like, Cameron, CD player? Come on, you've got to be kidding. Like what, were you like on some 1990s archaeological dig or something? It's like, oh, I think I found the CD player. This is a CD player, right? It's also a method. What does that mean that it's a method? Well, guess what? It takes something in, and the thing it takes in happens to be CDs. We have a little CD, Alice in Chains, always a good call. Apocalyptica. Any Apocalyptica fans in here? Yeah, a few. It's Metallica done on the cello. And Tracy Chapman, just to date myself. But what do? You take a CD, you put it inside here, you hit close, and you hit play, and out comes music. And the music that comes out of this thing depends on which CD you put in. But the interesting thing about it, if you think about it, is all of the electronics in here are completely reusable, right? I can use the CD player on virtually any CD. Right? Someday we might get to the day where you go to the store and you buy a CD and all the electronics to actually play the CD are inside the box, and you just plug your headphones into this and you just listen to your CDs. And then we toss away those electronics when we get rid of that CD and we get a copy of all the electronics again. That would be a huge waste, right, if you kind of think about landfill space and all that stuff. So why don't they do that? Why don't all the electronics to listen to a CD come with the CD? Because I can create them once and generalize them in a way so that if I pass in the right parameter, which is the CD, I can use the same thing over and over for all different kinds of values that go in, and as a result produce all kinds of values coming out. Okay? So that's the thing you want to think about in terms of methods, is you want to think about methods and defining what's going to go into them and what's going to come out of them in a way that's general enough that they can be used over and over again. And that's what the whole beauty of software engineering about, is thinking about that generality. Okay? So with that said, how do we actually define a method? Okay? So we need a little bit of terminology to think about how we define methods. Yeah, it's time for that dreaded terminology again in the object-oriented world. Okay? So when we actually call a method, right, you've seen this a little bit just like we did over there. We have what we refer to as the receiver, the name of the method, and then some arguments, which are the parameters, right? So here the receiver happens to be math. The argument or the method name is power, and then there are some arguments x and y that get passed in. Okay? The way we think about this thing is we say that we are calling or invoking a particular method. Here is the name of that method. So a lot of times you'll hear me say call a method. That's what we're referring to as invoking that method. What we pass to it in terms of these arguments is the parameters, what that function is actually, or that method is actually expecting. And you'll hear me sometimes use the terms function and method interchangeably, and they basically mean the same thing. And this guy can potentially give me back some value, just like square root and power did over there. Now, sometimes we always so refer to this, and you may have heard me say this in the Carol world, right, as sending a message to an object, right? So if we have our friend glabel, and I declare, let's say, I'll just call this lab to make it short, which is short for label, and I ask for a new glabel, and that glabel, I'm just going to give it the words hi at location 10, 10, just to keep it short and fit it on the board. And then I set its color by saying label, or in this case just lab, dot set color is color.red. Okay? So when I've done that, lab is the receiver, the method name is called setColor, and alternatively I would say that I'm sending the setColor message to lab. Okay? That's just terminology that we use, you should just be aware of it. So setColor is the message that we're sending. Okay? That's the receiver of the message. Same kind of thing as the name of the method and the receiver of that method, or making a method call or a method invocation. Those names just get used interchangeably. So how do I actually create a method in Java? Okay. Let me show you the syntax for creating a method. It's a little bit different, just slightly different than Carol, but actually very similar. And so the way this looks is I first specify the visibility. You're like, huh, what is that? You'll see in just a second. So we have the visibility, the type that the method may potentially return, what value it may return, the name of the method. All these have squiggly lines under them because these are things that you will fill in momentarily, and some parameters that get sent to that method. And inside here is the body, which is just a set of statements that would get executed as part of that method. Now, what do all these things mean? First of all, let's start with the visibility, which I'll just abbreviate as viz. The visibility, at least as far as you need to know right now, is either private or public. You're like, hey, yeah, I remember those from the Carol world. Yeah, and they're exactly the same. The way you want to think about it is, right now all you need to worry about is your run method is public, and pretty much all the other methods you write, as long as that method is only used in a single class, which is generally the class that you're writing that method in, they will be private. So for all intents and purposes, right now, all the methods that you're going to write, except for run, are all going to be private, and run has to be public. The way things are set up, you just need to make run public, because it needs to have a larger visibility, the way we've kind of defined the CS 106 stuff right now. And at the very end of class, like when we get to the end of the quarter, I'll sort of lift the covers on everything, and you'll see why. Okay? So that's the visibility. Private or public. Run is public. Most other things are private. All private means in terms of visibility is the only people who get to see this method are other methods inside the class that you're defining. Okay? So that's why it's visibility. It's who else can see it. Okay? The other thing you want to think about is the type. What's the type? The type here is specifying what gets returned by this method. So remember we talked about some methods, for example, that give you back something. Okay? It is the type of the return value. What does that mean? If I have some function that's going to compute the sign of something and you give me a double and it's going to give you back a double, its return type is double. And you might say, hey, but Marin, when I was doing methods with Carol, none of my Carol methods actually returned any values, right? Yeah, that was perfectly fine. And guess what word you used when they didn't return a value? Void. Yeah, that's a social. Good times all around, right? So void is a special type, which basically just means I'm not going to return anything, right? So its return type is void. It's like you're sinking into the void. You're getting nothing back from me. You know, that's it. It's kind of standoffish. But that's what it means, is I'm not giving you back a value. You need to know that I'm not going to give you back a value, so I still specify return type is void. Then the name, you know about the name, right? That can be any valid name for a method, just like we talked about in Carol. And then there are some parameters. The parameters are information we pass into this method that it may potentially do some computation on. So I'll show you an example of that in just a second, what parameters actually are and how we set them up. Okay? Some functions may actually have no parameters, like the functions you wrote in Carol, right? There was no information that got passed into those functions, in which case the parameter list was empty and all you had was open parens, closed parens, which means there's no parameters for this function. When you call it, you just say the name of the function and open paren, closed paren. Okay? So with that said, let me show you one more thing and then some examples. So you've seen a whole bunch of syntax so far, while loops, for loops, variables, declarations, all this happy stuff. And now I tell you, hey, there's these methods, and this is kind of how you write a method. And you're like, yeah, that has a lot of similarities to Carol. But there's this value that you're returning. How do I return the value? Well, surprisingly enough, you use something called the return statement, which just says return, and then after return, what's over here is some expression, which just could be some, mathematical, logical expression. And when you get to a return statement somewhere inside a method, that method stops immediately. It does not complete the end of the method and immediately returns whatever the value of expression is. A lot of times the return will come at the end of a method, but it need not come at the end. Your method, at the point that it's currently executing, will stop and return with that value that is expression as soon as you hit it. Okay? So that's kind of a whole mouthful of stuff. What does this actually mean? Let me just show you a bunch of examples, and hopefully this will make it a little more clear. We want some methods. Give me methods. So here's an example of a simple method. This is a method that converts feet to inches, right? It's kind of like, oh, Maron, yeah, this, yet again, an entirely useless thing for your $2,000 computer to do. But it shows you a simple example of all the pieces you need to know to write a method. What's the visibility of this method? It's private. It's only going to be used inside this class. What type is this feet to inches thing going to give back to me? It's going to give me back something that is of type double. The name of the function is feet to inches. What parameters does this function take? It takes in one parameter. The type of that parameter is a double, so what I'm expecting from you is something that's a double. It could actually be an explicit value that's a double. It could be a variable that holds a W inside it, but that's what I'm expecting is a double. And the way I'm going to refer to the double that you give me in this function is with the name feet. So all parameters have a type and a name, and the name is the name you're going to use inside this method to refer to that parameter. So what do? You give me some number of feet as a double, I multiply it by 12, and that's what I'm going to return to you. So when I get to this return statement, the method is immediately done, and it returns the value over here in the expression. Oftentimes, you're not required to, but I like to parenthesize my expressions to make sure it's clear what's actually being returned. So let me show you another example. We'll just go through a bunch of them.
Is it common to not put a comma as a separator for the type and then the name of the...
Well, the type and the name come together, so there is no comma there. Let me show you another example that actually has more than one parameter. Okay? We'll get to that right now. So here's a function that's the maximum function, right? Again, it's private. It's going to return an integer because you're going to give it two integers, and it's going to return to you whichever one has the larger value. So its name is max. It's going to return an integer, and what it's going to take is two arguments here, two parameters. Well, the first parameter, val1, is an integer, and val2 is also an integer. So the way I specify them is always they come in pairs. Type and the name that I used to specify, type and the name that I used to specify it, right? So val1 and val2 are both integers. What do I do inside here? I just have an if-else statement. If val1 is greater than val2, then val1 is the max. So right here, I'm going to return val1. As soon as I hit that return, I'm done with the method. I don't go do anything else, even though there was only an else that I wouldn't have done anyway. I return val1. If val1 is not greater than val2, then I return val2 because val2 needs to be at least greater than or equal to val1, so it's the maximal value. Okay? So again, if you have multiple, you can have as many parameters as you want, sort of within reason, right? I mean, within reason, I mean like sort of a few thousand. You can have as many parameters as you want. That's a lot of typing. They get separated by commas, and they come in pairs, value and the name that you use to refer to it. No, it will not print anything on the screen. All this will do is return that value to whichever place invoked this method. So if you think about something like readInt, right? readInt gives you back a value from, but it doesn't actually, I mean, that value happens to show up because the user typed it on the screen, but it wouldn't have printed it out otherwise, right? This doesn't print anything out. It just returns it back to where you sort of invoked this method from. There is, and we'll get to it in about 3 weeks. Yeah. So here's another one. This is something we refer to as a predicate method. And a predicate method is just our fancy computer science-y term for a method that returns a Boolean, right? A method can return any type you want. This one happens to return a Boolean. Private Boolean is odd. What does this do? You give it an integer, it tells you back, true or false. Is it odd, right? The name is pretty self-explanatory. So it takes that variable, computes the remainder after we divide by 2, and if that remainder is equal to 1, this whole thing is going to be true and it'll return true. If it's not equal to 1, that means it's equal to 0. In that case, this is false and it'll return false. So this whole expression here, again, because we have an equal, which is a logical operation, right? That's going to give us something back that's true or false, and that's what we're going to directly return to the person who called this function. Okay? So any questions about that? Alrighty. So let's look at something in a slightly larger context, right? Let's put this all together in a full program so you can get a notion of defining the class and defining the methods in it, and you can sort of see the whole thing as we build it up. So here's something called the factorial example program, and it just extends the console program. And all this puppy's going to do is basically compute some factorials from 0 up to max num. So we have some constant here, which is the maximum number we want to compute factorials up to. And if you remember, let's take a slight little digression to talk about factorial. So if you remember in your math class in the days of yore, there was this thing that looked like this, right? And you saw it and you went, oh, it's n, right? Yeah, hopefully caught your attention. This was actually n factorial, right? Yeah, the exclamation point totally different now. There's a couple people who were like sleeping. What was he talking about? N factorial, and all n factorial is multiplying all the numbers from 1 up to n. Okay? So 5 factorial, strangely enough, is just 1 times 2 times 3 times 4 times 5. And 1 factorial is just 1. And here's the bonus question, what's 0 factorial? Oh, I love it. Oh, it just warms the cockles of my heart. Yeah, it's 1. And there are some people who are like, but 0, you know, like, and they get all wound up tight, and they're like, no, man, mathematicians just said it was. So, because if you think about it, it's multiplying, it's starting with 1 and multiplying 0 additional terms, right? So I'm left with 1. It's a good time. So, how do I actually compute that? Well, in my program, I'm going to have some run method that's going to count from 0 up to max num and write out all the factorials. It'll say 0 factorial is this, 1 factorial is this, 2 factorial is this, by calling a method called factorial, passing in the value of the thing I want to compute the factorial of. How do I compute the factorial? Well, I just add some method. This puppy's going to return an int. Its name is factorial. It's going to take an n of the thing I want to compute the factorial of. And how do I do that? Well, I start off with some result that's value is 1, and I'm going to have a for loop that's going to count. Here's one of the few times as computer scientists we don't count starting from 0. We actually count starting from 1 because it makes a difference. We're going to count from 1 up to and including n. That's why this is less than or equals rather than just less than. So from 1 up to and including n. So there's still n terms I'm going to count through. What am I going to do? I'm going to take my result as I'm going along and times equals it by I, which means the first time I multiply by 1, store it back in result, then by 2, then 3, then 4, all the way up to whatever this n value was. And when I'm done doing this loop, I return my result, which is my factorial. Okay? Any questions about the factorial method by itself? Now, one thing that comes up, freaks people out a little bit. Don't get freaked out, it's okay. You see an I here, and you see an I there. And you're like, oh, we just did that thing with nested loops, Maron, where you told me that if one thing is inside another loop, like, I shouldn't use the same name. So why are you using the same name here? And the reason why I'm using the same name is to make a little bit of an example, which is that the I here and the I here are different I's. Okay? When you think about a particular method, a method can declare its own variable. So this result, its lifetime or its scope, is until we reach the end of the method down here. This guy lives inside this method. This I is an I that only lives inside the factorial method. It doesn't interact at all with the I outside here. So every method, and the interesting thing here is run is just another method. It just happens to be the special method that we always start executing from. But every method can have its own declared variables, and this I here is just its own declared version of I. It has nothing to do with the I up there. Okay? Question?
So is it possible to like give a variable from one method to the other method?
We'll talk about that in just a bit. So someone was wondering, is there a way I can sort of give some variable from over here down to over here? And I'll show you how you have to kind of think about that in just a little bit. Okay? But any questions about this notion of the same I, that this I is actually a different I than that I? When you declare a variable in the method, you're getting your own version of that variable in the method. It has nothing to do with the same named variable in any other method. Okay? Kind of a funky thing. That's just starting off the factorial, right? So if someone gives us 5, we need to start off by saying, we have some initial result, and then we're going to multiply that by 1, and then we're going to multiply that by 2. If we didn't have some initial thing we started multiplying, there would have been some unknown value there. And actually, Java would have given us an error because it doesn't allow you to use uninitialized variables. Okay? So this is kind of a funky thing, but important to sort of think about. There's a method in the context of a larger program. Variables within methods are not the same as the same named variable in other methods. That's the key take-home thing. Like, know it, learn it, love it, tattoo it backward on your forehead so every day when you look in the mirror, when you take a shower, you see it and you just know. Because that's one thing that trips people up. Was there a question up here?
So when you return results, does it get mapped into I? Is that why
Good question. So when I return here, what's actually going on? When I actually could say I'm going to compute the factorial of 5, okay? This guy comes in here, or let's make it easy. Let's say I'm computing the factorial of 2. So it multiplies 1 by 1, then it multiplies it by 2, I get 2. It returns this 2. What happens to the 2? That 2 goes back to the place at which this function was called. Where was that? That was up here. So this place up here where I said, hey, 2 question or exclamation point equals is what I would print on the screen if I was equal to 2 here, right? 2 exclamation equals. And then what's the value that I get back when I call factorial of 2? Well, it computes factorial of 2. It happens to be the value of 2. It just sticks in a 2 for whatever you had as the calling method. Okay? So you can think of when you call a particular method, the name of that method, think of it as getting replaced by the result that gets returned from that method. Okay? So if I run this program, just to make it clear, let me show it to you in its full glory over here. Here's factorial example. I'll go ahead and run it, and you can see what its output is. Factorial example. We're running, and there it is, right? So it says, if you can see up there, 0 factorial equals 1, because it writes out 0 factorial, right, in the code over here. It would write out I has the value 0 the first time through. So it writes out 0 factorial equals, and then it calls factorial on 0. And what it gets back from factorial of 0 is 1. So that 1 is just what gets displayed in the place of factorial 0, because that value I get back from factorial 0 is what's actually used here. And it keeps doing that all the way through the loop, right? So down here it calls factorial of 9, gets the value for factorial of 9, and returns that to the place where it's actually going to print it out. Okay? So let me show you one more quick thing. Okay. Which is returning an object from a function. Okay, so it turns out, interestingly enough, you can not only return like ints and doubles and booleans from functions, you can also return whole objects. So here is a method called filled circle. And what I'm going to give to this method is some x and y location for the center of the circle. Notice that's different than what a G-oval expects, which is the upper left-hand corner. I'm going to specify an x-y location, which is the center of the circle, a radius for that circle, and a color. And what I want this method to give back to me is an actual object that is a circle whose center is that xy. It has the given radius r, and it's filled in of that particular color. Well, how do I do that? Inside here, I say, hey, I'm going to create a new object that's of type G-oval, and I'm going to call it circle. And I'm going to get a new oval, right? And remember, oval expecting the upper left-hand coordinate for the oval. I want the circle centered at xy, so what do? I take that xy and I subtract the radius from the x direction and the y direction, which gives me the upper left-hand corner for the bounding box for that circle. And then I say, give me something that has a width of 2 times the radius and a height of 2 times the radius, because that's what defines that circle, right? It's the diameter is 2 times the radius in both the height and the width direction. So I get that oval. I've now called this circle because it's my new object. I tell that circle to be filled, because that's what I want to return as a filled circle. I tell that circle to set its color to be whatever color was passed in here. Notice the case sensitivity. Color with a capital C is a type. Color with a lowercase c is actually the name of the parameter that I'm going to refer to, and that's what I use here as lowercase c. So I set the color of the circle to be whatever color was passed in, and then I return this object. So that whole big box that contains this object that is some filled-in circle at that location, I say, hey, this is what you wanted because I'm giving you back a G-oval. Here you go, and I give you back the whole thing. Which means when you invoke this method, you better take the result and assign it to some place that's a G-oval, otherwise, or just add it to your canvas. You need to do something with it that you would normally do with a G-oval. Okay, you can't assign it to an int because an int and a G-oval aren't compatible. Question? Okay, yeah, you can't assign it to an int. You have to assign it to an object of the same type. Question back there?
Why are x and y set to doubles if the pixels are all whole numbers?
Good question. So I could have actually made this with ints, and I probably should have made it with ints. So that was my bad.
In the red method, how would you add that oval? Like, what's this like syntax?
So the way you could think of, let me just write it for you up here. So if I actually had the run method, so I'll public void run, and then let's say I had this function filled circle, right? So I call the method filled circle, and let's just say I want to put this at location 10, 10, and its radius is 2, and the color that I want to give it is red. Okay? Now, the thing that this gives me back is a goval object. There's a couple things I could do with it. I could declare a goval out here, call this O, and assign filled circle to it. And now I have the object O out here, which is actually that circle that this method gave back to me, and I can do whatever I want with it. Like I could say add O, and it would add it to my canvas. Alternatively, if I really wanted to, I wouldn't even need to set filled circle to some object that I want to keep track of out here. I'm just going to say, hey, you're going to give me a circle. I'm going to add it directly to my canvas. So anything that I would be able to do in my run method with a regular goval is the same thing I can do with this goval that's coming back from a method, because it's just giving me back a goval, and I can use it in the same way. Alrighty? I will see you on Wednesday then. We'll talk a little bit more about functions and methods then.